Hey everyone, and welcome to today's Explainer. We are digging into a massive, absolute game changer of a breakthrough in how AI handles highly complex, reasoning-intensive math. Now, you already know AI can summarize a giant PDF or draft an email in seconds. But historically, when it comes to the grueling multi-step logic you need for Olympiad-level mathematics, AI kinda hits a brick wall. Well, today, we're looking at the exact research that just cracked this problem wide open, using a brilliant new system. So buckle up, because this is literally going to change how we think about machine reasoning.
So, right off the bat, we have to understand the core mystery here. Why does standard naive AI retrieval fail so spectacularly at Olympiad math? I mean, if you ask an AI a fact-based question like what's the capital of France, it effortlessly grabs Paris from its data. Boom, done. But Olympiad math isn't about retrieving trivia. It's about pulling highly complex logical traces. Standard search methods completely fall apart here because they just can't surface the right mathematical traces in the right format. It's honestly like trying to find one specific gear for a Swiss watch by just aggressively scooping up handfuls of random metal from a scrapyard.
AI's math reasoning hurdle. Okay, let's dive right into this hurdle and unpack exactly what researchers were up against before this new system came along.
What's really fascinating here is what the research explicitly points out. Winning at AI math is much less about just bolting on a retrieval system and way more about discovering the absolute right retrieval policy. Just throwing a standard search engine at a complex math problem simply does not work. The AI gets bogged down or pulls totally irrelevant formulas. The researchers realized they desperately needed a system that could intelligently figure out how to search for the right stepping stones.
Introducing the meta-harness. And that realization brings us perfectly to the star of today's explainer, the meta-harness itself.
In the old days, which in AI time is like 6 months ago, human engineers spent just countless hours hand-designing these retrieval policies. They were trying to guess exactly how the AI should run its search. But the breakthrough detailed in this source material took a completely different angle. They went with emergence. Instead of micromanaging every little step, the researchers handed this meta-harness system a ridiculously hard set of Olympiad problems, and essentially said, hey, figure out how to search on your own. They literally let the retrieval behavior emerge organically out of the search process itself.
The optimization process. Let's walk through the workout montage phase of this research to see how they actually built this muscle.
You've got to check out this number, 500,000. To give meta-harness the foundation it needed, researchers built a massive retrieval corpus containing over 500,000 solved problems. And they didn't just carelessly dump them in there. The paper notes they painstakingly deduplicated and decontaminated these problems across 8 open-source datasets. They had to make absolutely sure the AI wasn't just, memorizing answers for the test later. So 500,000 clean, perfectly solved problems to pull from.
But having a giant library is useless if you don't train the librarian, right? The researchers used meta-harness to optimize a retrieval harness over 40 grueling iterations. They pitted it against a 250-problem search set of pure Olympiad difficulty math, pulling specifically from IMO-AnswerBench and ArXivMath hard. Imagine the AI trying, totally failing, tweaking its search strategy, and trying again 40 times over, just constantly sharpening its ability to hunt down those exact right logical traces.
Let's look closely at their exact pipeline. They started by initializing the search population for main baselines, things like zero-shot and few-shot prompting. Then, after those 40 intense iterations we just talked about, the system spit out 109 candidate retrieval harnesses. That's 109 totally different emergent ways to search for math solutions. Finally, they had to crown a champion. They selected a single winning harness based strictly on how it performed using a model called GPT-OSS20B. So, out of 109 contenders, one ultimate search policy reigned supreme.
Testing on unseen models. Now, a champion isn't a true champion until they're tested in the wild, against challenges they've never seen before. It was time for the ultimate boss fight. They took that single winning harness and threw it right into the deep end. They tested it on 200 previously unseen IMO-level problems. And the source material is super clear about how tough this was. These problems were pulled from highly advanced benchmarks like IMO-AnswerBench, IMO-ProofBench, and ArXivMath. The harness had never laid eyes on these specific problems during its 40 training iterations. And this is where the experiment gets wild. They didn't just test the winning harness on new problems, they tested it on entirely new AI brains. Aside from the GPT-OSS20B model they used for selection, they bolted this newly discovered search behavior onto 4 models it had never interacted with: GPT 5.4 Nano, GPT 5.4 Mini, Gemini 3.1 Flash Lite, and Gemini 3 Flash. The big question was, does this learned search behavior actually transfer over to completely different models? The impressive results. And this brilliantly illustrates the massive payoff. Let's get right into the data. All right, let's break down this comparison. The no retrieval method is our ground zero here. Now, interestingly, the researchers found that using dense retrieval, which adds an extra dense encoder, or using random few-shot prompting actually caused performance regressions. It literally made the AI worse at the math. BM25 retrieval, a standard lexical search, gave us a strong fixed baseline. But check out that bottom row. Metahexinus, operating entirely in code space on top of that same BM25 stack, outperformed the BM25 baseline by 1.3 points overall. It completely sidestepped the regressions that dragged down the other advanced methods.
But here is the absolute mic drop metric of the entire study, 4.7. The single discovered retrieval harness beat the no retrieval baseline across all 5 held out models with an average gain of 4.7 points. I mean, let that sink in for a second. Just by letting the AI learn how to search on its own, its ability to reason through the toughest math problems on Earth jumped by almost 5 points on average, even on models it was never trained on.
Just to prove this isn't a fluke, look right at the source material here. The pull-out box highlights this monumental success directly, stating, in retrieval-augmented math reasoning, a single discovered retrieval harness transfers across 5 held-out models, improving accuracy by 4.7 points on average over no retrieval. This proves that the emergent behavior wasn't just some lucky accident. It is a deeply transferable skill that fundamentally supercharges AI reasoning.
So, this leaves us with a truly profound question to wrap up on. We've just seen that when we finally stop micromanaging AI and instead give it a harness to learn its own strategies, it can literally conquer the highly structured, intensely logical world of Olympiad math. So, if an AI can organically learn how to hunt down the building blocks of the most difficult math problems on the planet, what complex, reasoning-heavy space is it going to master next? Code architecture? Scientific discovery? The implications of emergent reasoning are just endless. I hope this explainer has helped you see just how bright and fast approaching that future really is. Keep questioning, keep learning, and thank you so much for joining me.